solutions to part 1 of the chapter 13 homework, which deals with pressure and density. For problem number 5, you had a sphere and had a density of air inside of that of 1.4 kilogram per cubic meter. That's a little bit dense for air, but that's okay. And it says if the radius is halved, what will the density be? Well, if the radius is halved and the volume of a sphere is 4/3 pi r cubed, and that is somewhere on your formula sheet, then half the radius will be 1/8 the volume. And going back to the ideal gas law, which is basically this, it is P times V equals N times R times T. Then if these three factors all stay the same, N and R are constants, T is absolute temperature in Kelvin, then if the volume is 1/8 as much, then the pressure needs to be 8 times as much. So I just multiply that by 8. For P8, the answer I think in the book is incorrect for that. So it's asked, basically was saying what's the total inward force on a 1.1 meter diameter pilot sphere in which James Cameron sat. So first we need to find the pressure at depth. And since we're only asking about the inward force, we don't need to worry if there is atmospheric pressure or pressure inside the capsule. So atmospheric pressure is here plus rho GH or rho GD gives me this pressure. And then if I look at pressure here is equal to force divided by area, the surface area of a sphere is 4 pi r squared. And that is 3.80 square meters. I actually almost screwed this up because the book answer is wrong, and I second guessed myself. So that is 3.80. I will check to make sure that I say that. See if I can get that background to match. Yep, not bad. So the way that the book did it is it had 4/3 pi r cubed is the surface area. Well, that's for the volume, so that is not correct. So it is a high amount. For P13, what you've ended up says that a research submarine with a 20 centimeter diameter window, 8 centimeter thick. Manufacturers recommends the window can withstand this force of 1 times 10 to the 6 newtons. What's the submarine's maximum depth? So the pressure inside the submarine is at 1 atmosphere still. So we can take atmospheric pressure off of this, and all we need to figure is out the extra pressure caused by rho GD. So pressure is force over area. We can find the area of the window, pi r squared. Since it was a 20 centimeter diameter, 0.1 meter radius, so that's the surface area. Force over area gives me that pressure. That is equal to seawater times 9.8 times the depth, so that's 3,150 meters. This is supposed to be a person using this long straw. I don't even know what it looks like, an alien of some sort. So the pressure basically in the mouth plus the pressure caused by this column of liquid would have to equal the atmospheric pressure down here. So again, fresh water, rho GD, they said the person could pull it up 2 meters, and that equals atmospheric pressure. So the pressure in the mouth is less than the atmospheric pressure by 19,600 pascals. For P21, what we're asked to do here is we've got a cargo barge. It's 3 meters by 2 meters and sits 0.8 meters deep in salt water, and it's asking how deep it will be in the river. Well, since the river is less, fresh water is less dense, it should sit a little deeper. So overall, the buoyant force is equal to the volume displaced. So I know that that's the density of seawater. The volume displaced, it told me in the seawater was this amount, rho Vg, so that equals 484,512 newtons of water displaced. I normally wouldn't go that precise, but this is a midpoint of a calculation, so I'm going to keep it. and round at the end. So in freshwater, we know the boat has the same amount of mass, so it has the same amount of weight. So we have to push aside that same amount of weight of freshwater, but it's only got a density of 1,000 kilograms per cubic meter. So we're trying to basically find the depth of that. We know rho, we know g, the volume, 3 meters width, 20 meters length, times depth. And that would be 0.824 meters. Hopefully it makes sense. This is about 3% less density, and this is about 3% deeper. For number 23, you're given a 0.1 by 0.1 meter block and has a density of 700 kilograms per cubic meter. And in this particular case, it says it floats in water, which makes sense. It's less dense than water. What's the distance from the top of the block if the water is fresh or if it's seawater? Well, if it's, I don't know what I was doing up there. If it's fresh water, again, I'm going to use my density equation. Rho equals m over v, mass equals rho times v. I get that this block would be 0.7 kilograms of mass. So it has to displace 0.7 kilograms of water. Again, I could have everything multiplied by g in here if we want. So that says the depth would be 0.07 meters, 70% underwater, 30% out of water. So that really should be 0.30, not 0.03. Thank you for double checking that, Doug. Goodness gracious. Good enough-ish. Okay. So 0.030 meters out of the water. In seawater, we still have the same mass displaced because it's the same block. So it's 0.7 kilograms, but now the density of seawater is greater, so the depth is going to be less. So now 0.068 meters is underwater. So, God, I did it again. 0.032 meters would be out of it in the salt water. Dag nabbit. Anyhow, that's that. Hopefully those make sense other than my algebraic, it's not algebraic, it's arithmetic. Stupid errors there. And I'll end up posting this and then do part 2. Thanks.